Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about various classification approaches for object recognition in relation to computer vision and many other tasks. Last lecture, I started our discussion on neural network, artificial neural network. We will continue that discussion. So, if we look at the architecture of the artificial neural network, which we are considering in this particular lecture, that is multi-layered feed-forward network. And I mentioned that in this case, the input is processed layer-wise. So, you have the input layer, then it is processed, and these neurons which are connected to the input layer, they produces the output. Those output also becomes the input to the next layer. So, this is the next layer, and then in this architecture there is another layer which is called output layer. So, from the output layer you get the output. Now, you can see that the connectivity of any particular node from its previous layer in such a way that all the outputs of the previous layer, they are connected to that node. So, we call it fully connected multi-layered feed-forward network. This layer is called hidden layers, intermediate layers are called hidden layers, and the final layer is called output layer. We have also discussed that how the input could be mathematically, we could model the input-output relationships using the corresponding weights of connections and representing them as in the form of a weight matrix, and then particularly the output relation can be expressed from any ith layer. There is a weight matrix corresponding to that ith layer, and which is multiplied by the input from the i-1th layer, which is the input vector, which is actually the outputs of the i-1th layer. And then there are also biases of individual neuron. So, they are also added with respect to this. So, this produces that weighted sum, effectively weighted sum of some vector for all the neurons in that layer. And then finally, we apply a nonlinear function in every component of these column vectors. So, this could be represented in this form. This is the processing at the ith layer from the output of the i-1th layer. And in abstract form, if I represent this processing in a pipeline, so it shows that there are several layers. Each layer is characterized by its parameter set by the respective weight vectors which are connected to neurons from the previous layer, and also the biases of every neuron. So, these are the two components of parameters for each layer, and successive layers, these are processing in the cascaded manner, and then finally you get the output. So, the objective of this model, objective of this problem is that we would like to tune these parameters. We would like to get that set of parameters which will maximally corroborate the input-output relationships or input-output specifications what is given. So, you have a training data set, and then in the training data set you have the corresponding specifications given in training example or training input vector, you have its corresponding output vector. And your model, you try to design your model in such a way to get a set of parameters which is represented here by this notation of big W, and so that you get the output. So, it's an optimization problem, and we define the error of this kind of fitting as we did earlier for least square error fitting. We can define this error in this form. A square error is basically least square errors that we have shown here, and this is a function of the parameter. So, we would like to get that W, that set of parameters, which will minimize this error. And as we discussed earlier also, what we need to do, we need to apply the gradient descent procedure and the same procedure what we have discussed to obtain the solution. So, this is a summary of that optimization problem, and the steps are similar. So, it's an iterative optimization. Start with an initial weight vector or parameter, I should say, it's not single weight. The whole set of weight vectors that is denoted by this. This is the initial notation. And then we update these parameters by using the respective computing gradients at those points, and moving, since it's minimization problem, we move along the negative direction of the gradient. So, it is effectively, it can be written in this form, and this is the step size, and this is the gradient computed because you have this square. You can see that this minus gets consumed with the minus, it becomes plus, and the gradient of this first component would be this. After that, you take the gradient of this function. So, this is how the gradient should be computed. But as you understand that it's a multidimensional parameter space. So, computing gradient is non-trivial, and you have to do it using some kind of computational approach instead of going through any analytical approach. So, there are certain efficient computational approach. There is an efficient computational approach by which you can compute these gradients, and this approach is called backpropagation algorithm. And in the previous cases, though there is a summation of all these accumulated gradients of the total training examples, but what we can do that for each training example, immediately we can update the weights. Then we call it as stochastic gradient descent, because we can take the input sample in various order randomly, and your weight updation is dependent on that kind of randomness. So, and finally, when it converges, then you take that solution. Now, let me elaborate further this gradient computation, and we will see that how this backpropagation algorithm is designed, exploiting the chain rule of gradient computation. So, first we will consider a very simple case where let us consider you have a single neuron only, and there the inputs are n-dimensional input, as you can see. These are the inputs to that neuron, and these are the weights which are connected to the neuron. Each input is connected through these weights. That means weights are multiplied there for each input, and also there is another parameter W naught, which is called the bias term, and which is added with the weighted sum of the input. And finally, this resultant sum, that weighted sum plus the bias, it is non-linearly mapped using any nonlinear function, and I can say any function. Instead of saying nonlinear, it could be linear function also, but usually in neural network we use nonlinear function, and then you get the output. So, your error of these computations, let me write it in this form, that's just that's the square of the difference. So, T is your specified or we call it target response, specified value given this input. So, given this input, its corresponding specified value is T. That is the training example, that is the data set, training data with respect to this input. So, and O is the computed one at a particular value of these parameters, at a particular value of these parameters. So, the error becomes T minus O whole square. So, what you need to do? You need to compute the gradient of E with respect to all these weight vectors, or individually we have to compute the gradient of E with a particular, say, Wi, say ith vectors, so partial derivatives. That means keeping all other fixed, you can compute it. Now, one simple way you could have computed using some kind of numerical simulation, which means that let me consider, say this is my xi, this input is my xi, and say this is connected with that weight Wi. So let me perturb this Wi with a very small value, say delta Wi. Then and keep all other weights fixed. So we are changing delta Wi. Then we also observe what is the change in the output. So naturally, the estimate of this would be, estimate of this would be, as you understand, that the difference of O, difference of W. So you can compute directly. So this is basically forward direction computation. So you are computing the functional values. So we call it forward direction because in multilayer perceptron there is a direction from input to output. So you just compute one by one sequentially from one layer to another layer these values, and finally you get the output. That is the forward direction computation of this function, of this particular processing. So you have to compute twice. First you have to compute using Wi to get O, and then you should compute or get, if I say yes, that O would be always fixed. Say if I compute once, that is fine, because then for each weight I have to perturb using a small value, and then I should get this one. So there are two processes. This process is very simple, and this also can give you the gradient vector, but there are few issues here. So one issue is that it's an approximation. So if we could have got some analytical expressions at this with this model, then this estimate would have been more accurate. So there is some inaccuracies involved in this process itself. The second problem is that you can see that how many times you are computing for a single gradient vector. So for a single gradient vector, you are computing n times. So you are computing n forward directional, n forward passes are to be there. So that is computationally very intensive. And if you consider training with a very large network, there are millions of parameters, hundreds of thousands of parameters actually, even millions, it goes to millions of parameters. Then you understand that this is not tractable, this is not computationally feasible. So instead what we do, we go for an approach where we can perform some analytical model for that computation. That means given the values of x1, x2, xn, and given the values of weights, parameters, and also bias, we would like to exactly, precisely compute what should be the gradient with that value, and that too with an efficient. So the backpropagation algorithm, what it requires one forward pass just to get all the results, intermediate results from each neuron, all these results, and then using them, it computes from backward directions, from the output to the input, it computes individually each and every gradient of the parameters as it moves along the connectivity. For each connectivity is characterized by a parameter, say weight, and also each neuron is also characterized by the bias weight. So as you move from output to input, you are computing them one by one. So that is why backpropagation algorithm is very efficient and it is widely used in this case. So let us try to understand the backpropagation algorithm with respect to this particular neuron. So by applying chain rule, what we can do here, so we are planning to compute this, and you can see that with respect to this neuron, what if I apply chain rule, first this output, this error should be the gradient of error with respect to the output should be. So it should be derived with respect to O by applying chain rule. Then this variable O should be derived, should be derivative of O should be derivative of O with respect to Z should be computed. Then derivative of Z with respect to Wi should be computed. So that would give you the full thing. Now you know that you can compute it analytically. That's the advantage, because what is delta E delta O? So you can see that it is nothing but it is 2 into T minus O. It is minus 2 into T minus O, right? What is delta O, delta Z? Now O is basically Fz. So which means this component would be F dash Z. So it depends upon the function. If you have an analytical function, you can compute its derivative. For example, say fz is a ReLU function. So if it is ReLU function, given the value of z, suppose the z value is here, we know that its fz would be equal to 1 at this point. So derivative is 1. And if the value of z, for example, in the negative directions, we know that derivative would be 0. This is a singularity. So that we are not expecting to occur. So these are certain cases which we assume that they won't occur with your computations. Now if they occur, you have a problem, right? But anyway, so f dash z also is in analytically, so f dash z equal to 1 if value of z is this, or equal to 0 if value of z is there. So you have an analytical function. After that, when you are computing partial derivative or rather z, partial derivative of z with respect to wi, we find that this is a linear combination. So only this component xi should be there. So if I write it, it is minus 2 into t minus o, then f dash z or gradient of fz, gradient of function f, and then xi. So that is what the product of these three is delta e, delta wi. So this is fine for of course single neuron. Problem is that when you have a network of neurons, now these computations at each node, and then the output of each node is also dependent of several input from other nodes. So the derivatives get accumulated from various sources. So we'll see that how actually those things could be computed in our algorithm. Algorithmically you can compute them. So just to show you these steps once again clearly. So as I mentioned, this is minus 2 into t minus o. This is f prime z, or this is derivative of the function f with respect to z, and then derivative of z with respect to wi. So naturally, given this expression, sum of wi xi plus w naught, that is the functional form. So only term related to wi is wi xi. So if I take the derivative, it will be simply xi. So finally, it is the product of these three will give you this function. Now, when you have a functional function like sigmoid function, it has a beautiful property which can be also used in these computations and which will simplify the thing. Actually, this property is that this f prime z it can be expressed in terms of the output value only. So you can see that this is a derivation. So you can write f prime z as the product of fz into 1 minus fz. So fz is O here. So we can write this thing as that this thing can be written as O into 1 minus O. So this means I can write it as say minus 2 into t minus O, O into 1 minus O, and then wi. Note that this is O because I have used O, don't confuse it with 0. So, so this is how these computations can be done analytically. So given these values, I can simply use these values and compute it. I don't have to do any numerical simulation to compute the gradient. Now let us proceed to see that how this computation can be used for the network of neurons. Right. So we apply chain rule from output to input, towards input, and from output layer to, that means towards the input layer. So compute partial derivatives of weights at I minus 1th layer from the partial derivatives of ith layer. So that is the trick. So till that point you are computing it a bit like dynamic programming concept. So from the output layer you start with, because using chain rule, the first thing you should do the derivative with respect to your error function with respect to the output variable. Then from there again the outputs should be derived with respect to their dependent variables, what is there at the output layer, and it propagates like this. So let us see with this particular diagram, let us see how we are going to consider these things. Suppose you have a forward computation, already you did the forward computations and you notate the response along each node. So, I have just shown some of the responses, because what I have considered here, say if I consider the respective, say this weight, say this weight is say W31. So, I have already shown, say you know that my convention was that the third neuron in this layer is connected with the first neuron of the next layer. So, it is W31. So, I would like to compute the partial derivative of E with respect to 31, right. So, that I am like to compute. So, what are the dependencies for computation? What are the changes if I perturb this W31? What are the values which are going to change? You see that this value is going to change because of this, and since this value is input to these nodes, so these two values are going to change. Again, these two values will change also the output. So, finally, of course, now these changes will propagate. So, when we are computing the derivatives with respect to W3I, actually if I compute derivative with respect to O, or first from E to with respect to O, then from O with respect to this and with respect to this, and from each one of them with respect to this, and then it propagates, and then we can compute the whole thing. And these computations have been shown here. So, you see that how this is propagated. You first compute delta E, delta O, that is this at this part. Then when you are accumulating here, you are computing delta O with respect to delta Y13 and delta Y13 with respect to delta Y12. Similarly, delta O with respect to delta Y23 and delta Y23 with respect to delta Y12, and these two gradients are added here. And finally, this is the change with respect to delta O with respect to delta Y12, and then so this equivalently, this is giving you the change of delta O with respect to delta Y12, and then you get delta Y12 with respect to delta 312. So, and when you are computing, as you understand that each one can be obtained through analytical value through this value. So, if I assume that suppose these are all sigmoid function. So, T and O is given. So, at this point, delta E, delta O, we know this value would be, let me write it here, say as I have shown, -2 into T minus O. What about delta O, delta Y13? That means this to this. So, there you have to consider, first there is a nonlinear function. So, it will be as you can see that it would be basically at this point, since this is nonlinear function. So, it is f dash z. So, since this is output O, so I will write O into 1 minus O, and then this is multiplied by the respective weight here. So, this is the first neuron and this is the first neuron. So, we will write it here as, in this case, we will say write W114 in our convention. So, this multiplied by W114 and will give you the respective derivative with respect to Y13. And from delta Y13 to delta Y12, once again, here also you get the respective gradient. So, Y13 into, so here it would be Y13 into 1 minus Y13, that is propagated for due to nonlinearity, and again the weight, multiply this weight. Finally, so in this way you compute everything, and finally this one, as you see, this is the derivative with respect to W31. So, what is connected here? So, what is it? What is the product of these two? It is Y31 is getting multiplied with it. So, this value should be Y31. So, let me show you also with a cleaner diagram. Okay. So this is what is computing, the delta E, delta O, then this one is delta y13 with respect to delta y12, then delta y23 with respect to delta y12, then this one. So this is further elaborated once again, that process. So this is delta E, delta O, this is delta O, delta y13, this is delta O, delta y23, this is delta y13, delta y12, similarly this, and from there you compute it. So you can also see that how individual, say for example delta y23, delta y12, so say this one, delta y23 with respect to delta y12, this derivative. So there is a nonlinearity. First you have to derive the get the derivative of the nonlinear function, and then you get the derivative relationships. So because this is a weighted sum, you get the derivative with respect to that. So this should be equivalent to multiplication of these two terms. So as you can see, every component can be computed from the responses whatever you have obtained in the forward pass. Every component can be computed like this, and you can efficiently do this computation. Instead of going through this kind of sequential pathwise, we can do it layer wise. So first I will compute this in this layer, then I will compute this, because this two if I compute, from there I will compute this one, I will compute this one with respect to this, and then that means with respect to all these derivatives, and then we will be computing all individual. So while computing itself, we are computing the respective gradients. So there is a rule which is called delta rule, which is actually considering accumulation of the derivative. So what it considers that you consider at any point, suppose you want to compute the derivative of error with respect to this at this point, and you have already computed the derivatives in the previous layer. So whichever the layer it is connected, this derivative should be sum of the respective contributions along this path, which means this is derivative, say, so we will say delta, so this is with respect to, this is what is delta E, delta y12, this we are computing. So you can see that what you are doing, this you have already computed, this you have already computed here, and then with respect to that you are just multiplying, you are multiplying this part. Actually if I multiply delta E, delta O, this part has been already computed, and then you are just simply adding, you are simply multiplying with the nonlinear functions and also the weights. So this is the way you are doing it. So this is expanded here. You can see that this term is expanded into this form. Now while doing delta rule, actually we will be using the composite values, and because this value will be also product of these values, this is already computed. So at this stage, to get the derivative of E with respect to the with respect to their delta y12, it is sufficient that say this is one delta component, say delta 1, and this one is delta 2. So delta 1 into f prime z13 plus w113, and again delta 2 into f prime z23 to w123, they are added, and that would give you this error delta E, delta y12. So this is actually called, this is called delta rule of the computation, right? So that's what I am saying. Okay. So instead of that, I have just considered the nonlinearity also to be composed there. Actually delta E, delta O also is multiplied here, because it's common multiplication. The whole thing should be considered delta, because delta by definition means delta 113, by definition it means delta E, delta y13, and delta 123 is delta E delta y23. That means a gradient of error with respect to this point and gradient of error with respect to actually, since we are computing this, I should say gradient of error with respect to this point and this point, whatever way you can consider it. I have a better diagram, the next slide. See, this is more clearer picture. So at the ith layer, you have all these computations, neurons, and delta is the respective derivative with respect to error at this point. So it is, say, delta E at this point, whatever this node would be there. You can say this neural node, just input at this node. I can write, say, delta n1i or something like. So you are getting this. This is the delta. So naturally, the accumulated point would be W weighted sum of all these deltas. That is what you are getting, and that becomes the derivative with respect to delta ym at this point, at the I minus 12 layer. So accumulated gradient value from output to this point. You have to then multiply with f prime z. Yes, it is there. It is multiplying with f prime z. So if I consider at this point, it is already considered. So delta value is accumulated gradient value at this point. So multiply with the respective gradient of the nonlinearity function, and then those you multiply with the weights, and sum of them will give you respective. So this is what you will get. Will give you the corresponding derivative at this point. So now you understand the backpropagation rule. That means from the output we are computing each delta. So each delta at that point, which means the derivative with respect to error at that point at the output end of any neuron. From where you get also derivative at the other point, and while doing these things, you are also computing the respective derivative with respect to the weights. Because when you are computing the derivative of weights, there what you are doing there, you are simply multiplied with the input value. You see that delta mk, so this is the weight, say this is the weight, it is multiplied with this value. Actually, this is not, because it is accumulated, it is not required. You just multiply with this. So this would give you the respective value. So when we train a artificial neural network using this method, now we understand that same algorithm I am just repeating with respect to backpropagation algorithm. So you initialize the weight, then for each training sample where you have the specifications of xi and oi, then you compute the functional values of each neuron in the forward pass, then update weights of each link starting from the output layer using backpropagation, and continue till it converges. So there are some of the tricks by which you can improve the convergence, because as you know that since your network is very large, and initialization is a very important thing to do, and sometimes when you are in the initial stages, when you are taking this step, sometimes it may come out of a good local minima and it may jump into a bad local minima regions. So what you can do that to avoid, so that's what gradients can change abruptly in consecutive iteration. So you would like to have a smooth change of this gradient value. So instead of taking the point gradient, what we do, we take a running average of weight updates to be added with that gradient. So instead of considering the point, the change of weight only at that point, we take the running average, and that is how this running average, you can see at the tth iteration, you are also taking some change, whatever change you have computed at the t minus 1th iteration, you are taking some part of its contribution, and then you are also adding the corresponding change whatever you get at that tth iteration. And this is called basically, this technique is called momentum based parameter updation. And the value of, you see that eta, its learning rate, and this learning rate also can be varied. So initially this learning rate could be high, but later on you can decrease it, so that you get a smooth convergence. So one of the methodology, one of the thing we can do like this. So at the initial stage, you have certain learning rate if it is reduces. Otherwise, if the error is not reducing, so you just look back at the tth iterations, what was there back at tth. I mean, before tth iteration, what was the error? If it is reduction, then you go ahead with positive step. Otherwise, no, there is a negative direction. So you get some kind of adaptiveness while moving along that space. So one of the thing that we need to understand about this particular model, say though we discussed this model initially with respect to classification, but as you have seen here, we considered a target function. Rather, we are trying to match with a target function. So given certain input, there is a functional value. We are building up model which will try to match with those functional values. So this problem can be is also considered, this is a regression problem. Basically, this is a regression problem. And for classification, we consider the absolute class indications there. So there are certain ways this neural network is finally, as you have seen, that it is giving a values which is in the real domain, and naturally it is more suited to a regression problem. So there are certain ways by we convert it into a classification problem. We will see later on. So, but primarily it is a regressor, and build a model to predict functional value effects given input x. Now, one of the way you can convert to a classifier by appropriate encoding of classes, but there has to be some kind of policy, because exact matching of that function may not be there. So some kind of quantizations, etc., needs to be considered when you are encoding into the discrete levels of those vectors. For two-class problem, you can have, of course, binary encoding of 0, 1 or one-hot encoding of 1, 0, 0, 1. And one thing we consider actually that when you have a output, for example, let me consider this one-hot encoding. Suppose there are two classes and you are getting the values here, output values here. This is output neuron. So this is basically the output neurons, and there you are getting the responses from each neuron. This is the first neuron, so this is the second neuron. And let me consider this output is, say, y1, and say this is y2. Now you expect, if you are trying to simulate, that one of them would be 0 and another would be 1, but it will never happen, and you can use some quantization. But instead of that, there is another way we interpret it. We consider that we can it's a kind of logistic regression problem, which I am not going to discuss here, but it is trying to estimate a logarithm of the probability of that class. Say this is a class omega 1. So it is trying to estimate the posterior probability, what I have discussed earlier. So these probabilities, actual probabilities, are computed, which is called the principle of softmax. So here it is e to the power y1 by e to the power y1 plus e to the power y2, and similarly the other one. So these are the softmax probabilities, and from those you can infer what is the class level. So these are certain things which is also followed in the case of neural network. Now I will discuss a typical problem. I will just as a case study, and this is a problem of measuring hemoglobin from images of blood samples. So, you see that your input is an image, and in the image, what you have here, you have the blood sample on a tissue paper and you take the image of it. So, I will come to that system. So, the steps are like you collect blood sample from a subject and then collect a drop of collected sample on filter paper, and then you do image processing, because you see that color is an important information, because the blood is red, and the kind of the saturation and hue of that color should be related with your sample, even the intensities also. So, there first we do some color corrections for normalization. So, we use the color constancy algorithms what we discussed during color processing. So, it is white patch algorithm. We have used this gray level, that is average of gray levels we use for white patch algorithm. Then we identify region of interest by Otsu's thresholding. So, we identify the respective region of interest there, and that we do in individual, in the color channel itself, and from there actually in the intensity image. We convert it in the intensity image and use the Otsu's thresholding technique to identify the region of interest. And after that, we perform a simple featured descriptor, feature computations. Just you see that we calculate the mean red, green and blue value, intensity values from this region of interest. Then we that becomes our input feature vector. So, input feature vector is 3-dimensional feature vector. And then we design an artificial neural network with certain number of layers, and there is an output which will estimate the hemoglobin. So, it is a regression problem, because it is quantifying that is hemoglobin in gram per deciliter. Actually, these input training samples are to be created, as you understand, and that needs to be created with a lot of care, with proper protocol, proper experimentation in the laboratory. And once you have those training samples with respect to filter papers, images of filter papers with blood drop and respective hemoglobin amount. So, now you can train the classifier. So, this is the example which is showing that how you can measure the hemoglobin from images of blood sample. I mean, this is an imaging system. In our system, it is an embedded system. We have used Raspberry Pi camera, and you can see in the imaging system, this is a placement of filter paper, and there is an illumination, controlled illuminations by which this imaging is taking place. So, this is the processing for color correction. So, you have this is the input image and this is the output image, and from there you get the region of interest. Of course, we are showing the input image once again, not the output input to here. This just shows that now our data set and also its characteristics. You can see that we collected about 344 blood samples of 86 patients, which means there are number of blood samples per patient, and these patients having varied distributions of hemoglobins. Otherwise, if you don't capture that distribution, it is meaningless. You cannot learn. So, you have to learn this. In one way, you are learning this distribution or the functional mapping. So, this is the neural network model, and you can see that we considered 5 layers and 11 neurons in each layer. So, 5 layers, and in each layer there are 11 neurons, and this model has been empirically derived. So, which means these are called hyperparameters of models. So, number of layers and number of neurons per layer. So, we varied, and finally we have found that what is the best what we could get within that variation, and we are doing. There are some techniques by which you can do grid search and other things by which you can choose the hyperparameters. And finally, the output layer, from the output layer you are using a, see, each one has a ReLU, which means that we are only considering linear response in the positive side. It introduces also nonlinearity. And from the final output layer we are getting the hemoglobin content. So, For performance analysis, one thing we do, we reduce the error of observations for a single instance. So that means we take multiple observations of the same subject, which means when we take the blood drop, we take multiple filter papers and take images from them. So, and then you report, instead of doing point measurements, you report mean and standard deviations or standard error of that measurement. And what we get actually, average standard error, we get 0.22 gram per deciliter, and the range varies. This is the range 0.02 to 0.75 gram per deciliter. And mean absolute error with respect to the gold standard cyan methemoglobin method, that is the laboratory method, we found that 0.75 gram per deciliter, that was the mean absolute error in our experimentation. We have correlation coefficients with those values, high correlation like 0.91, and also the coefficient of regression, because it's a regression problem. So, how much of the variance is accounted for? So, it is also quite high, 0.82. This is a graphical plot by which we show that how the predicted value and actual value, they are quite corroborated, and this shows the scattered plots of the error values. Now, when you evaluate a performance of a classifier, that was a regression. Of course, regression problem, we know that sum of squared errors, that gives one kind of performance, and then the coefficient of regression is also another parameter, another measure, evaluation parameter. But classifier, particularly these two class problems, there are few metrics which are very often used, and those are called actually they are called sensitivity, specificity, precision, recall, different terms. But to understand them, first let us understand what is meant by true positives, false positives, true negatives, and false negatives. So, in our case, anemia is the positive case. So, a subject having anemia means it's a positive case. So, when we consider the ground truth, so true positive is that the number of samples which are truly predicted as positive with respect to ground truth. False positive, on the other hand, that means it is predicted positive, but actually it was negative samples. So, number of such samples false positive. Similarly, true negative, it is predicted truly negative with respect to ground truth. And false negative, once again, it was a positive sample but predicted negative. So, the numbers can be shown in the form of this matrix we call sometimes as confusion matrix as well. So, the accuracy is a metric which is defined in this way: number of true positive plus true negative, which is true predictions, divided by total number of cases. Similarly, precision is total number of true positives divided by predicted. So, what is the fraction of your positive prediction is true? So, that is precision. Similarly, what is the fraction of your ground truth positive samples are true? That is called recall. So, and sensitivity also, it is also basically recall. And then there are true positive rate, which is defined again, that's a true positive by say same sensitivity or true positive rate, and specificity is basically true negative rate, which is basically fraction of true negative, predicted true negative with respect to the actual ground truth. And F score, sometimes these are combined, a composite score, sometimes it is useful, because sometimes you can have very high precision but low recall, and high recall and low precision by varying certain parameters. So, F score actually takes a balance of this. So, harmonic mean of precision and recall, which is defined here as you can see. So, that is also sometimes used. Now, in the anemia detection, in this case, we considered by considering the standard medical knowledge, that normal population who are not anemic, who are normal, who are healthy, their hemoglobin level should be more than 12.5 gram per deciliter. And if I consider pregnant women, it should be greater than 11 gram per deciliter. So, for that we got normal populations, the whole population, sensitivity 82% and specificity 80%. and for pregnant woman, sensitivity 89.4% and specificity is 94%. Actually, this application was meant for screening anemia cases of pregnant women. So you can see that the performance with respect to pregnant women, that is quite satisfactory. So further, what we did, we validated this on a new data of 64 volunteers, the same technique we have used. But of course, for validation also we required to have the ground truth. And there we found this is the minimum, this is the mean absolute error, 0.78 gram per deciliter with respect to gold standard measurement. Correlation coefficient is 0.88, regression is 0.77, down than the training samples and test data also. Then normal population, it was sensitivity is 92%, specificity is 85%. So it is quite good for normal population. For pregnant women also it is sensitivity is 93% and specificity is 78%. But specificity got down, which means that true negative prediction that was not as per expectation. So finally, let me summarize this particular topic on classifications. As we see, classification is a task of assigning a known category or class to an object, and typical classification approaches that what we discussed, they are naive Bayesian classifier or even the Bayesian approach we discussed. Then k nearest neighbor classifier we discussed, linear discriminant analysis we discussed, and also artificial neural network that also we discussed. So with this, let me conclude my talk here and this particular topic. Thank you very much for your patience and listening.